Welcome to this video of aspireforgmat.com. Before attempting this question, please take the practice test at www.aspireforgmat.com and then verify your answers against this video, which will be available after you answer the question at our site. The link for the free Aspire for GMAT course is also available in the description box below. Just register on the site and enroll for the course. There are many such tests available. If you have any doubts or queries that you would like us to clarify, post in the GMAT forum and we will answer your questions. Our instructors can also solve these problems in a video which will be available at our site for your benefit. Okay, the next problem we're going to deal with is this one. It says, does the integer k have a factor p such that 1 is less than p is less than k? Now we know for sure that for an integer k to have a factor p such that 1 is less than p is less than k cannot be a prime factor. So what this question is indirectly asking for is, can k be a prime factor? If it is a prime factor, it won't have any other factor other than 1 and itself, so there will be no factor p. And if it's not a prime factor, it will have a factor p, which could be between 1 and k. Now these are the two conditions that are given. The first is k is greater than 4 factorial and the second one is this one. So let's see how we're going to solve this problem. This is one of those questions in which there's no basic rule. All you need to know is what is prime factor, what is a non-prime factor, and I mean how do you define prime and non-prime numbers, and how do you work with those numbers. You would have to basically there's no formula, you just have to expand it and think upon it. So how we're going to solve is this, like this. This is how we would deal with it. We're given information that k is an integer and we are asked whether 1 is less than p is less than k, a value, so a p, so that 1 is less than p is less than k exists. So what the question is asking for is, is k a prime factor or not? In case it is a prime factor, this value p would not exist, and in case it's not a prime factor, this value p would exist. So let's see the two conditions that are given to us. The first one says k is greater than 4 factorial. Now 4 factorial is something simple that you can solve. So k is greater than 4 factorial, so it must be greater than 4 into 3 into 2. 4 multiplied by 3 multiplied by 2, that's 24. So k is greater than 24. Now just think of any prime factor that is above 24. Now 29 is a prime factor, 31 is a prime factor, 37 is a prime factor. So there are prime factors and there are non-prime factors like 25, 26, 27. All these are multiplied by some of the other numbers, and therefore a p does exist which is less than this number k but is greater than 1. So there is such a p. So if we go around step by step and try to solve it, for example, let's take k is equal to 25. It consists of factor 5. So there is a p called 5 which is less than 25 and greater than 1. Similarly, if you take a prime factor greater than 24, for example, k is equal to 29, then there would be no p that exists, and therefore we get two scenarios using this particular condition, one in which p does exist and one in which p does not exist. So this particular condition or this particular statement does not tell us enough to confirm whether p exists or not. So this is insufficient. So the moment we find this insufficient, let's just go and pick out the wrong options or pick out the impossible options. We know a cannot be possible because a says that b should be, 1 should be right. D cannot be possible because D says that 1 and 2 should be individually right. So now it has got to be something between B, C and E. So if we see B, it says 13 factorial plus 2 is less than k is less than 13 factorial plus 13. This is very interesting. How do we know whether all the numbers between 13 factorial plus 2 and 13 factorial plus 13 are prime or not, or whether they are all non-prime or whether all of them are prime? How do we know that? Firstly, you cannot, there is a problem here, you cannot expand 13 factorial, it's too big. It's just not possible to calculate all that multiplication, calculate that big number in that short time. So the moment you find something really tedious to do, you know for sure that's not the answer, that's not the way you're supposed to approach. So you're 100% sure you don't have to expand the 13 factorial and literally multiply it, because it's too tedious. So you don't multiply it. Now, the other thing that actually you could just think of is that prime factors don't happen to come continuously. Just try to think of any prime factor that you know. If there is a prime factor, if there are two numbers or three numbers or even a set of numbers, every odd number in that would every even number in that would actually be a non-prime factor. It would be divisible by 2. So 13 factorial plus 2 to 13 factorial plus 13, if c 13 factorial plus 2, okay, it's less than k. So k is actually ranging from 13 factorial plus 3, it includes 13 factorial plus 3 and 13 factorial plus 12, because it's less than 13, so it has to be 13 factorial plus 12. Now between this 3 and 12, consider that 3 is prime, then 4 would be non-prime because it would be even. If 5 is prime, then 6 would be non-prime. If 7 is prime, then 8 would be non-prime. So there would be definitely non-prime numbers in this. What we need to know is whether there are prime numbers in this. That becomes the question, because we for sure know that there are non-prime numbers in this. We need to know whether there are any prime numbers in this. How do we figure that out? Now, we know 13 factorial is equal to 13 into 12 into 11 into 10 and so on till 1. So it is divisible by all those numbers, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. It's divisible by all these numbers. Now, when I write 13 factorial plus 3 divided by 3, is it divisible by 13 factorial plus 3? What do I see here? I see that this particular thing inside the inner bracket, this is divisible by 3 because it consists of 3, and I see again that this is also divisible by 3. So I can divide them. When I say something is, when I want to find out divisibility, I know 3 is divisible by 3. I just have to divide it by 3. If this is also divisible by 3, whatever I get, that is 13 factorial divided by 3, whatever I get plus 1 would be my answer. So if this is divisible by 3, whatever this number is, if it lies between 1 and 13, I would be able to divide it by all numbers between 1 and 13. This whole number, that is 13 factorial plus this, would be divisible by 3, or would be divisible by that number, whatever comes here. For example, if I take 13 factorial plus 4, I know this whole thing, 13 factorial plus 4, is divisible by everything between 1 and 13. And I know this is not divisible by 2 and 4. So let me just check whether this is divisible by 2 and 4. This is divisible by 2 and 4. So I know it has prime factors, or factors between 1 and itself that can be divided, or that can be a factor. So if I take something like 13 factorial plus 5, 13 factorial plus 6, everywhere I would see that there would be a number, the number coming in the latter part of this expression here, the number coming here, it would be 13 factorial would be divisible by this number, the number itself would be divisible by that number, and therefore I would always have a factor between 1 and this and 13 factorial plus whatever number. I would always have a factor there. So I find out that all numbers that are lying in this range are definitely non-prime, and therefore this is sufficient, because it tells me that all numbers lying between this are non-prime, and therefore there is a factor called p. I don't care what that p is. That p is different. It has different values for different, because this is a range, it has different values. I don't care about that. All I do care about is that such a number p exists, and that's enough for me. So you've got to be very careful while reading such a question, because all this question asked you for us whether such a p exists. If you see such similar questions we've done before, they asked for a value of p, and because we were not able to determine a value of p, we were just able to determine a range. We decided that it was not good, we couldn't work with it, it was insufficient. However, here what is asked for is whether such a p exists, and we are able to determine that such a p exists. So this is good. It's sufficient. We are done with this question. So we know that B is sufficient, A is not sufficient. So C says that both of them together will be sufficient. We don't need it. We know that 2 is sufficient by itself. E says that individually or together they are not sufficient. We still know 2 is sufficient. So we don't want E. So the right answer at the end is going to be